Some of you have asked me about a good reference to read measure theory from. So this is a wonderful resource. These are all the notes by Professor B.V. Rao, who is the best teacher that whom I ever had in any institute. So he taught this class, and these are all his notes. They are wonderful. And my approach is very much similar to this because he is the same professor who taught me. So I do not know of any better resource than this. So here is a quick recap of where we stand. We started with S, a set. Then our first attempt was a measure defined on all subsets of S. We quickly found out that leads to problems. So we dropped certain subsets. We came down to some subsets of S. And then we saw that we just cannot drop subsets arbitrarily. There must be some coherence in which subsets we keep and which we do not keep. For example, if I keep A, then I also have to keep A complement. If I keep A and B, I should better also keep A union B. So counting all those things, we had a name, sigma algebra of subsets of S. Now, sigma algebra is a nice thing. It's a collection of sets that has the whole set, the empty set, and it is closed under countable union and intersection and complementation. But there are so many different sigma algebras, ranging from the absolutely trivial sigma algebra, which consists of just these two sets, and ending with the most complicated, the power set. So that is the simplest and that is the most complicated. The question is, which one do I pick? We have already seen that this didn't work because it leads to various contradictions. If we go to the other end of the spectrum, then it is true trivial. You can hardly pose any interesting question in terms of this. Say if you are interested in probabilities, this has probability 0 and this has got 1, nothing in between. So closer to this you get, the math becomes simpler, but it also becomes less interesting. The closer to that you get, the math becomes more interesting, but eventually you lead into contradiction. So naturally, people try to get hold of some optimal trade-off. Now, Arie Lebesgue, who kind of started this entire discussion, so he came up with one thing here, so which was smaller than power set, but much larger than this trivial thing, which was called the Lebesgue sigma algebra. Now his aim was this, he was working with R, and his aim was to define length for different subsets, and he ran into the same problem. He could not define length for all possible subsets. He tried to look at the smallest class, he tried to look at the largest possible class of subsets for which he could define length in the natural intuitive way without running into any contradiction. And the largest sigma algebra for which he could do this, he called that, he just proposed that sigma algebra, and we call that now as the Lebesgue sigma algebra. While that is a nice thing, and it also comes with a theoretical guarantee that this is the largest that you can work with, move one step further and you run into contradiction. But this beast turned out to be rather complicated. So if I give you a certain subset of R and ask you, is this A inside your Lebesgue sigma algebra? In general, the answer will be very complicated. It is not at all easy to check whether a given set is inside that sigma algebra or not. So people do not use that much. Instead, we have relaxed it a little further. We come somewhere here. We use what is called a Borel sigma algebra, which is closer to the trivial thing. So it is even smaller, as a result easier to work with, but still rich enough so that you can pose all interesting mathematical questions in terms of Borel sigma algebra. But the way I have shown, you can see that Borel sigma algebra is smaller than Lebesgue sigma algebra, so there are sets which are not in this but in this. But if I ask you to come up with one such example and give you 1 month, you will not be able to come up with one unless you are a genius. So we hardly lose anything of practical value by restricting our attention from Lebesgue sigma algebra to Borel sigma algebra, and this is what most people work with most of the time. Now we are going to exactly define Borel sigma algebra and give the motivation behind it in the next video, but for the time being, let me just discuss the way Borel sigma algebra is constructed. We shall go into the details in the next video, because this way, this general way, is useful for other purposes as well. The way Lebesgue came up with his sigma algebra is something that I like to think of as supply-based approach, whereas Borel's idea was going down the demand-based approach. So let me give you a simple analogy. Suppose you have gone to the market. Now you want to buy certain things. So here is one way of going about it. You make a complete list of all the things that are being sold in the market. And then start thinking, what are the things that you do not need? So you think, I do not need paint, I do not need hairpin. And in this way, you come up with a list. So that is the supply-based approach. You first made a list of all the supplies, all the possible subsets that there are, and then you are trying to throw them out only if you really have no use for it. The other approach is the demand-based approach, is what we do most of the time. In this approach, we first make a list of our demands, what we really want. So it's a much smaller list. We want fish, potato, rice, oil, and then we go into the market and buy exactly what we need, instead of looking at all the things that I could have bought. So this is the demand list, this is the supply list. Now this is a much smarter way of approaching, and that's what basically Borel did. He did not start by listing all the possible subsets and then scratching his head, figuring out which one should I drop and which one should I keep. He started by saying which one are the things that I must have. And then he constructed a sigma algebra starting from that. Well, the details will come in the next video.